Alright, so in the previous video we implemented the method of simultaneous equations to solve a system of ordinary differential equations, and in this video we're going to solve another system, but this time it is going to be non-homogeneous. So instead of having 0 on this side, we're going to have functions of t. So we're going to employ the same method as before, so we want to somehow equate the top and the bottom so that we can get rid either of the y or the x. So the best thing we can do here, for example, is if we want to get rid of the y, we can multiply the top by d. So if we multiply the top by d, which is the differential operator here, we're going to get a term for dy. And obviously, because this is a derivative, it is going to act on the function of t here. So the derivative of that is going to be 3t squared. And now if we group it together with the bottom equation, so I'm just going to subtract this. This is going to become plus x equal to minus t. Now what we're going to do is we're going to add these terms together. So this one is going to cancel out with that one, so that gets rid of the y's, and we're left with the following. So d squared x plus x equals to 3t squared minus t. So this is second order non-homogeneous ordinary differential equation with constant coefficients. So in order to solve it, what we're going to use is a method of undetermined coefficients that we have learned before. So the first part is obviously finding the homogeneous solution, which is going to have the form c1x plus c2x. So sorry, it should be two solutions there. So we're going to find the characteristic equation of that. So that's going to be r squared plus 1 is going to be equal to 0. And this is going to lead to r minus I, r plus I equals to 0. So because the roots are both complex, we are going to have a solution of the following form. We're going to have c1 e to the power of it plus c2 to the power of minus it. And in previous videos I mentioned why when we have complex roots in the characteristic equation, we can essentially write the solution in this form using complex exponentials, or we can write them down using cosines and sine functions. In this case, it would be more convenient to use this because we're going to have to differentiate this function then to find y, and this is a lot easier to differentiate and then to manipulate algebraically than if we use trigonometric functions. So that's the reason why I'm going to use this form in this particular example. So this is the homogeneous solution. Now what's going to be the solution related to this? Well, that is going to be big X, and we're going to choose a polynomial with undetermined coefficients that is of the same order as this polynomial. So we're going to have a2 squared plus bt plus c, and should actually make this bigger to show you that it's a different solution. So now we're going to have x prime is going to be equal to 2at plus b, and x double prime would be 2a. So now that we have this, we can plug this back into the original equation here and then solve for those coefficients. So we're going to have what? 2a plus at squared plus bt plus c is going to be equal to 3t squared minus t. And as we have learned before, undetermined coefficients consist of finding those constants, the values of those constants, by grouping them into terms that correspond to the same power of t. So in this case, we have this term and that term. They should be grouped together. A and c should be equal to some constant. So in this case, the constant is 0. And finally, bt is going to be corresponding to this particular one here. So let's see what that gives us. Well, for the constants, we're going to have 2a plus c equals to 0. For at squared equals to 3t squared. Well, that's very simple. We have a equals to 3. And because of that, that implies that c is going to be minus 6. And finally, for this one, we're going to have bt equals to minus t. So that implies that b is going to be equal to minus 1. So now that we have that, we can plug back into the original equation here. So that means that our x of t, big X, is going to be equal to 3t squared minus t minus 6. So now that we have those two things, we can pretty much just put them together to find the solution for x. So I'm going to go back here. So our general solution for xt is going to be c1 e to the power of it minus it plus 3t squared minus t minus 6. And now what we're going to do is we're going to take the derivative of that, so dx. So this becomes c1 minus ic2 e to the minus it plus 6t minus 1. So that implies that from the system of equations that we have here, we can actually solve for y using the first equation. So that's going to be equal to y is going to be t cubed minus d of x. So that's going to become 3 cubed minus I c1 e to the power of it plus I c2 to the power of e to the minus it minus 6t plus 1. So that's y. Now what we want to do with this is we're going to apply it to the second equation. Oh, actually that's just the final solution, right? So this should be our final solution. But what we want to do with this now is if we want to prove that this solution and this solution are both correct at the same time, what we can do is we can find dy. We can find dy such that once we plugged it into the second equation, we can verify whether we get the correct answer. So dy in this case is going to be 3t squared minus 6. So I'm just going to put it on this side. And this is going to be what? Well, this is going to be I times I. That's minus I squared. So I squared. I squared is minus 1, but then it is times this minus here. So that's going to be plus. And the same thing happens here. We're going to have a plus c2 e to the power of minus it. So that's going to be dy. And if we plug it back into the second equation, which is this one, so dy minus x should be equal to t. So let's show that that's true. Well, we have our dy here. If we subtract x from it, this would go away with that. This 6 would go away with that. Then we would have these two terms will cancel out with these two terms. And in the end, we're going to have minus t. So that's going to become positive t. And that proves that this solution is correct. Now we can use the same method and we can apply it to the first equation to show that it also satisfies this one, and in this case it does. And I recommend you try to do that just so that you can verify for yourself that this is actually the solution to the problem. And you notice that there are some imaginary units here present, but in general this is how you would go about solving a system of two ordinary differential equations. And this is quite useful in some cases because what does a system of differential equations like this represent? Well, you may have a system in which you have two populations competing for the same resources. So it could be something like an ecosystem where the two predators, there are two types of predators that are competing for the same prey. So obviously the dynamics of the system is going to be modeled by this coupled system of differential equations, and that's why you will want to solve it, to see how those two systems are competing together. In the next video, we're going to talk about how to solve higher order differential equations, and we're going to employ methods that require reducing the equations to a system of first order differential equations.